I'd like to start with a thought from a great philosopher, since that's where I come from. This is Spinoza, the Tractatus Politicus. He was addressing the philosophies of those who had come before him, but you can see that it's equally relevant to many that came after him. So the question is, how do we talk about ethics, in particular about the social contract, without writing satire? Well, I like to invoke some great spirits. Look around the room. This conference is full of ideas for naturalizing the social contract and advances in naturalization of the social contract. We've heard lots of them. I won't tell you who to look at, but you can choose. I'd like to also pay homage to comrades that are not here. Bob Sugden, who was an early Humean, invoking evolutionary game theory in social contract theory, and Ken Binmore, who has a number of books on game theory and the social contract.
Can you turn up the volume a little bit for your voice? I think you are talking a bit too soft.
All right. And here is a lively picture that should bring out a lively voice. It's Lynn Ostrom, who uses both evolutionary game theory and lots of empirical research. So I would think that if you want a capsule answer to how you avoid writing satire in social contract theory, you use evolutionary game theory, broadly conceived, and you use empirical research. What can I tell you in an hour? A real naturalistic scientific theory of the social contract is a big enterprise, and we don't have it right yet. So what I'll give you in this talk is a cartoon theory of the social contract, and the purpose of the cartoon is to give some general outlines. It could be refined in lots of ways and supplemented. And also a scaffolding from which to hang some nuts and bolts for the theory of the social contract, without thinking that these are only nuts and bolts that you would use. As I said, some other nuts and bolts have been floated already in this conference. So here's my cartoon. There are two fundamental problems of the social contract. The first is coming together to cooperate to produce a surplus over what would be produced if individuals went their own ways. And the second is the problem of dividing the surplus. Okay? You could, if you wanted to, collapse these into one problem, or you could expand them and add other things like division of labor. But I'll keep it at this level for the talk today. And if you're looking for simple games to analyze, to encapsulate these two problems, I think the best that you can do for simple two-person games is to model the problem of cooperation to produce a surplus with a Stag Hunt game, and model the problem of dividing the surplus in a bargaining game. And of course, we like to go from 2 to n persons, but it's easier to analyze two-person games, and there's a little bit that can be said about n-person games. So first thing I'll talk about is the Stag Hunt. Second thing I'll talk about is bargaining. I'll talk about these by themselves as games. There's a danger in doing this, because if the social contract has these two aspects, it might be that if you put them together, you get something different than you get from the two parts, And that's true. So I'll say something at the end about putting them together. So the Stag Hunt game, as most of us know, was introduced by Rousseau. It takes coordinated cooperative activity to hunt a stag successfully. If one of the stag hunters decides to hunt a rabbit, one person can hunt a rabbit successfully by themselves, right? So there's a problem of trust. If you don't trust the other guys in the stag hunt to hunt the stag, there's no reason why you should join the stag hunt. The stag hunt game appears in various forms in Hume's treatise. Hume talks about the evolution of conventions in a famous passage in which he talks about the rowboat. Two men row in a rowboat. Their actions are coordinated even though they've not made any explicit promises to one another or even discussed it. Cooperation just arises naturally, was Hume's point, but of course if you think of the rowboat, it's a stag hunt game. If the other guy's not rowing, then there's no reason for you to row. If the other guy is rowing, then there's a reason for you to go. So there are two equilibria in this game. Here's a prototypical stag hunt game in case there's anybody in the room who hasn't seen it before. I doubt that this is true. Rows pay off against column. Cooperators do best, of course. They get a 3. If the other guy defects and you cooperate, you get a 0 because you can't hunt the stag successfully or row successfully if you're the only guy doing it. On the other hand, if you decide to go it alone and defect, you get the same payoff no matter what the other guy does. You get a 2. And so from the point of view of safety, it's better to defect, but from the point of view of optimal payoff, it's better to cooperate. There's a tension between these two considerations in game theory, a tension between the risk-dominant equilibrium, which is for everybody to defect, and the payoff-dominant equilibrium, which is for everybody to cooperate. So that's my little model of the social contract, right? If you're not in the contract and the other guy isn't, nobody else is in the contract, then it pays for you to stay out, right? That is, the state of nature, whatever it is something that's an equilibrium, right? If you're in the contract and the other guy's in the contract, then it pays for you to stay in. Right? So the fundamental problem of getting to the cooperative equilibrium is a problem of trust, because if you can't trust the other guy and you think, well, it's just as likely that he'll not cooperate as that he does, then you shouldn't cooperate. And if he thinks that you're thinking that way, he shouldn't cooperate, and nobody cooperates. So that's the Stag Hunt game, and that's a quick reason why I think it's a good model of the social contract. I could say a lot more, but I won't unless you ask me. There are generalizations to n-person games which are quite interesting. There's the game 3 in a boat, 2 can row, introduced by Taylor and Ward in 1982. The title is self-explanatory. Right? If one guy is rowing in the boat, it's best for you to join him and make 2 row, because then you get the optimal payoff. Okay? But if 2 guys are rowing, it's best for you not to row, because the third guy doesn't do any good, just gets in the way, and he works hard. Right? This is interesting because it adds the free rider problem to the stag hunt problem. Right? If everybody's cooperating, it's best to free ride. Okay? But that doesn't mean that you get driven all the way down to no cooperation at all, like you would if you were modeling things as a prisoner's dilemma, or as the Economist's public goods contribution game, which is a generalized prisoner's dilemma. Right? There are 2 equilibria, just like in the Stag Hunt game, or more than 2, but 2 kinds of equilibria. There's the equilibrium where nobody rows, and there are equilibria where 2 row and the third doesn't. Okay. if you go to in-person public goods provision games of the kind that everybody knows and add a threshold, then you get a generalization of 3 in a boat, 2 can row. The threshold is you can't produce any public good until you get a certain number of contributors, right? And then above that, well, you could say like 3 in a boat, 2 can row. Above the threshold, the other guys don't do any good. Or you could say there's some increasing function you do a little better if the other guys put in, but you get nothing until you get to the threshold, right? There are various versions of this. But they all create, as well as non-cooperative equilibrium, partial cooperative equilibrium, where, because of course if you're right near the threshold, right, it's better for you to jump in and make the public good than to have everything fail. Okay? So these are pretty rich models if you want toy models of the social contract problem. The fundamental problem of the institution of the social contract, something that exercised Hobbes and others, is how we get from the non-cooperative equilibrium to the, or a, cooperative equilibrium. It's not so easy, right? In the first case, they're equilibria, right? So by definition, if you're there, you stay there, right? Well, you might add some noise, some random noise to the system, mutations or some kinds of shocks to the system. This is investigated in 2 related but rather alternative models by Kanduri and company and by Peyton Young in 1993. The Kanduri paper is a finite population model with mutations. Young is stochastic replicator dynamics, so it's an infinite population model, but with random shocks interposed on it. And the idea of these things is, if you have a little bit of noise, then you really can get bounced from one equilibrium to the other if you wait long enough. But for certain kinds of games, it may be that you spend almost all of your time in one equilibrium. So this is the notion of stochastic stability that's introduced in these papers. And in the Stag Hunt game, it turns out that the stochastically stable equilibrium is hunting hare. Right? So this is a model of how social contracts can fail. Right? It's a model of the dissolution of the social contract. Well, that's okay, because social contracts can fail, right? And we don't want to write satire and pretend that everything always comes out right, okay? But they don't always fail, so there must be something more going on that we have to think about. So I'm going to discuss 3 mechanisms for cooperation and their role in the institution of the social contract. And they're not the only ones by any means, but they're the ones I'll talk about. First is signals. Second, local interaction. And on a spatial grid or maybe on a network. And finally, adaptive networks where the networks are dynamic and network structure evolves, as well as strategies of players on the network. These have already been made an appearance in your talk, right?
Do all of these assume that the game is given to you as opposed to the mechanism design question? Could you change the game a little bit in order to get an enforceable contract?
Well, as you know, both you and I have written about evolution of the game too, but that's not on my agenda for this talk. But that's certainly very important.
I'm thinking, because 2 slides back, your example made me think of the meeting Don and I went to last year, where there was discussion of how you get international agreements where you have to have a certain number of people playing in, and you might change the rules of the game so that so that nobody could get a benefit from free riding or something of that sort?
You could, and those are interesting questions. But and I could say more about interaction of that with the dynamics, but I'd like to hold off on that.
Sure.
Okay, so one, signals. Signals with no pre-established meaning are in particular what I'm interested in. And of course, David Lewis has the distinction of inventing signaling games. Not often philosophers actually contribute to science, but at least these days. But David Lewis invented signaling games, sender-receiver games, where there's no pre-established meaning, and where the question is, in these games, where you get from a no information transfer state to a state in which information flows from the sender to the receiver in the games. But I'm not, and these games, if you look at them closely and investigate various dynamics, turn out to be much richer and more complicated than you might think on the surface. But I'm not going to talk about that. Today, in connection with the social contract, I want to talk about the use of costless pre-play signals before the Stag Hunt is played. So players exchange signals. Okay? They may not have any pre-existing meaning, but they exchange signals, and they can condition their play on the Stag Hunt on the signal that's received. And that's a picture of Art Robson, who wrote a paper introducing the notion of the secret handshake. The subtitle is Darwin, Nash, and the Secret Handshake. And the idea of this paper is that if you're at a non-cooperative equilibrium that's stable, it can be destabilized by the introduction of pre-play signals. Right? If there's a signal that isn't used by the natives, then you can have mutants who come in, or innovators who come in, who send this signal. Okay? If they don't get the signal, they play just like the natives do. So they play like the natives against the natives. Okay? But if they get the signal, they play optimally against each other. Okay? That means they can invade, even in Prisoner's Dilemma. So it destabilizes stable equilibria. Okay, that's a deep idea and has been followed out in many ways in the game theory literature. Let's see, and I said that. It's also true that pre-play signals create lots of new equilibria in the game. But something I want to call attention to also is that if you look at dynamics, say in replicator dynamics, just adding pre-play signals changes the size of the basin of attraction of different equilibria. Oop. Okay, so I looked at the Stag Hunt game. Stag Hunt game has two strategies, so we just give the players two signals, and they exchange signals, and they play the Stag Hunt game. You run this through replicator dynamics, starting at randomly chosen population proportions. And without the signals, the basin of attraction is much bigger for hunting hare. That's in fact why it's the risk-dominant equilibrium and why it's the unique stochastically stable strategy in this game using Peyton-Young or Kanduri. But if you add these pre-play signals, the size of the basins of attraction flip. And then about 70% of the basin of attraction goes to stag hunting. So these signals are doing something. Those are simulation results, although you can see something behind them if you look at all of the equilibria that are created by the signals. Lots of the non-cooperative equilibria are destabilized by the secret handshake, right? Whereas none of the cooperative equilibria are. It's much easier to get to cooperation. But of course it doesn't tell you yet that you can get from everyone hunting hare to everyone hunting stag, because you can't. Right? It's just that it's now the size of the basin of attraction has been shifted, so if you put in these random shocks, right, then in the long run they'd go the other way. You might look at this in terms not of replicator dynamics and infinite population, but in terms of finite population evolution. And there is this paper with Jorge Pacheco, Francisco Santos in 2010 that does this pre-play signaling in the stag hunt. And it turns out that it works quite well in the finite population, which is no surprise. But it also turns out that the more signals, the better. So if you have lots of signals, you're almost guaranteed to get to the cooperative equilibrium. Okay? So signals, even though they're cheap and you can say whatever you want to in the signals and so on, in an evolutionary setting seem to make a very big difference. Let's see, there is some experimental economics literature in pre-play signaling in stag hunt games. I cite these two, one recently by Bloom and Ortman and Jett, which show that this result seems to work also in the economics laboratory. 2, local interaction, right? I'll move on to local interaction. And now it's local interaction on a fixed spatial or network structure. Lots of people have done this, have investigated local interaction. Thomas Schelling starts it with a segregation model. If you're talking about local interaction promoting cooperation, the first paper that I know of, and I'd like to cite it because very few people ever talk about it, but it's by Gregory Pollack in Social Networks. Social Networks is our journal at UC Irvine. Gregory Pollack was a graduate student when he wrote this thing on cooperation on a viscous lattice. Novak and May in Nature, of course, Eschel. And, okay. So the local interaction model I will show you is local interaction with neighbors. So this is on a square lattice, and you interact with your neighbors. Of course, we need to choose your neighborhood. So here we'll choose north, southeast, and west, northwest, southeast, the Moore 8 neighborhood. That can help stag hunting, but it just depends on the parameter values what happens. So the white guys are stag hunters, and they're doing okay. We threw a few of them in at random, right? And they've established their colonies, but they're stuck, right? That just runs it again. So it does something, right? But isn't a cure-all, because it can get stuck with some stag hunters and some hare hunters. Here's a further development, really due to Eschel, Elon Eschel, and others. And that's that there are two neighborhoods, the interaction neighborhood and the imitation neighborhood. The interaction neighborhood is the neighbors with which you play this game. The imitation neighborhood is a neighborhood that you look around and see which strategy is doing the best on average, right? And you imitate the strategy that's doing the best on average. Or if you want to imitate the strategies in proportion to how well they are doing on average, either one works, and lots of variations work. in this game. Oh, I should say, of course, there is the biological counterpart, where instead of an imitation neighborhood, you have a reproduction neighborhood. And reproduction neighborhood might be bigger than the interaction neighborhood if you throw your seeds out. Right? And could be smaller, and Simon has a paper that talks about the effects of this. So let's have two neighborhoods, and suppose we make the imitation neighborhood bigger than the interaction neighborhood in the same game that we had before. Well, here are the stag hunters. They're just taking over, right? Because the hare hunters that are outside now can see inside the group of stag hunters, right? They imitate, right? Stag hunters get imitated around the periphery where the hare hunters can see the stag hunters, and stag hunting takes over. If you transpose this into the biological setting, you have the same sort of argument. If you reverse the size of the neighborhoods, you've got something that favors spite instead of favoring cooperation. Here's a third idea, and let's see. There was the idea of a leader that was floated. Who floated that earlier? Simon's floated that. Okay. So there are leader-follower games. There's a paper by Peter van der Schaaf and Jason Alexander in Philosophy of Science, right? Now I know the room is full of scientists and nobody reads the Journal of Philosophy of Science, but that's where it is. And they had the idea that it's wrong to think of everybody as the same, right? There may be some people that are much more influential than others. And when we think of mutations or inventions in a cultural context, if the influential person makes an invention, then his followers will immediately adopt it, right? Although if it turns out to be a dud, right, then gradually the other stuff may creep in. But that creates islands. That also makes it easier to get out of those frozen states that I showed you in the plain vanilla local interaction model. Okay. This all depends on the dynamics that I chose, which was imitation dynamics. Economists usually like best response dynamics, and that's a different story, right? So the imitation dynamics is what goes with differential reproduction. And if you do differential imitation or differential reproduction, this works. So I don't want to claim that more than there is there. Okay, now I want to move on to dynamic networks or adaptive networks. And I'll report some work that I did with Robin Pimentel, that's a picture of Robin, on adaptive social networks. First with two-person interactions in this PNAS article of 2000, and then later on in three-person interactions, in particular three-person stag hunts in later articles in mathematical behavioral sciences and stochastic processes and their applications. And then there's a related article quite recently by Santos, Pacheco, and Leonards on dynamic social networks. And actually, there are lots of articles on dynamic social networks. But I'll tell you about ours. The idea is that we have network formation by reinforcement. And the model looks like this. There's a small group of individuals. So in contrast to the big networks that we saw earlier, this is a small network model. There's a small group of individuals. Each day, each individual picks someone to visit, goes out and visits him, has an interaction, and goes home. And the probabilities of visiting evolve by reinforcement learning. In particular, the kind of reinforcement learning that's used by Roth and Arev for those in the room that do that kind of thing. Mathematically, each individual has an urn with a ball of a different color for anybody they might visit initially. If you visit somebody, you get an interaction, you take your payoff and add the number of balls of that color to the urn, right? In proportion to your payoff. So your urn accumulates historical payoffs, and your probability of visiting somebody is proportional to the accumulated payoffs of visiting them in the past. And it takes a little work to see how the limits are of this process, but I'll show you. This is a stag hunt with this dynamic social network. We've got 3 stag hunters and 3 hare hunters, and what happens is if you can see it happening before it cycles, you start out with everybody visiting everybody else with the same probability, but the arrows between stag hunters and hare hunters fade out. That is, stag hunters, the limiting result is that stag hunters visit stag hunters and hare hunters visit hare hunters. Once stag hunters visit stag hunters and hare hunters visit hare hunters, within those groups, you can have any probability distribution of visits as long as it's symmetric. A visits B with the same probability that B visits A. Okay. Well, if you have this network formation by reinforcement dynamics, where stag hunters and hare hunters end up segregating from each other, right? We can add to this process strategy revision by imitation. Right? Everybody looks out around and sees who's doing well in the group. Once in a while, right, according to some clock, right, and revises their strategy. Well, now we have 2 processes, and they can run on different time scales. I think Simon talked about 2 time scales too. So this is 2 processes can run at the same time scale, but let's look at the 2 time scales. If the network formation dynamics is fast, so that you have fluid networks, and strategy revision is slow, so that only every once in a while does somebody revise their strategy, then you end up with everybody hunting stag. Okay? Because stag hunters find stag hunters, hare hunters find hare hunters, stag hunters convert to hare hunters. Hare hunters look around, see stag hunters are doing better, convert, right? And then rapidly learn to associate with other stag hunters. So everybody gets converted to stag hunting. If the relative speeds of the 2 dynamics are reversed, then you get the reverse. Right? If it's a frozen network, right, and fast strategy revision, then you're back in the original dilemma, right, where random interactions favor hare hunting, right, because it's safe. And of course, that doesn't mean you always get hare hunting, because it's a small finite group. So you might get lucky, right? But more often than not, you'll get hare hunting. Oh, there are actually some experiments. Let's see. Did I say this? I said that. There are actually some experiments in the economics laboratory done. One that's sort of in the area was by Page, Putterman, and Unequal in 2005, where they had individuals sort themselves into groups. So it wasn't quite this dynamic network. But quite a recent one by Rand, Arvisman, and Christakis and PNAS is pretty close to what we have here. Not quite the reinforcement dynamics, but they can make or break network ties. The same result, that if you have fast network dynamics, then these guys sort themselves, and slow imitation dynamics will convert you to stag hunting.
Just real quickly, what happens if you just use the earn model, not to decide who to play with, but to decide whether to hunt stag?
Okay, great question. There is a double earn model where you use the earn model for both. And basically you get the same results. The numbers aren't quite as dramatic, but basically you get the result that fluid networks favor cooperation, frozen networks favor non-cooperation. I have that model in my Stag Hunt book. It's a good model because you don't want it just to work because we cherry picked the two different dynamics. Okay. Second part of the social contract problem is division of a surplus. So that's bargaining, right? But I want to just talk about the simplest bargaining game, bargaining with perfect symmetry. Okay? So here's a Nash bargaining game, except you're dividing some good, say, let's see, economists say divide the dollar, right? Or a cake or some good, and your utility is linear with respect to this, and all anybody cares about is the amount that they get, right, in terms of their utility function. So there's perfect symmetry between the players. That's all there is. This is called, well, I called it divide the cake. It's often called divide the dollar. What happens then? Well, if you believe Aristotle's theory of justice, Aristotle should come back again one more time. Justice is proportionality, and since there's nothing to choose between these two in terms of the perfect symmetry, they should get the same amount. If you think about John Nash's axiomatic characterization of the Nash bargaining solution, the first two parts of the characterization, the symmetry and efficiency postulates get you the equal split. So what happens in terms of evolution of the equal split? Well, I should say first, to set the stage, it is a problem because although we know what the answer should be from various perspectives, if we think of the bargaining game, there are an infinite number of equilibria. And if we think of the bargaining game in terms of evolutionary dynamics and run the replicator dynamics on the bargaining game, a discretized version of the bargaining game, we don't always get the equal split. We get the equal split maybe 68% of the time, and then we get other stuff, right? We get, in our populations, if we do replicator dynamics, we get 60-40 split, or, you know. How do we get that? Well, we get some people in the population demanding 60%, some demanding 40%. The 60%ers, when they meet each other, get nothing. When they meet the 40%ers, they get 60%. 40%ers always get 40%, right? And there's some population polymorphism that makes this an equilibrium. So from an evolutionary standpoint, too, there are an infinite number of equilibria. So there is something to think about. Well, if we look at the mechanisms, the three mechanisms that I rehearsed in talking about getting to the cooperative solution in the Stag Hunt game, more or less everything works here in getting the equal split. First, remember that noise caused problems in the Stag Hunt game. It always caused the social contract to fall apart, right? But if you add noise to the bargaining game, to this bargaining game, you always get the equal split. Okay? And that follows from much more general results that Peyton Young got in 1993.
Any level of noise?
Well, this is stochastically stable equilibria, so the result is, as the level of noise approaches 0, the probability of being in an equal split state of the population approaches 1. We want to say it carefully, it's like that. Of course, if you have a lot of noise, then you can't always be in any state. You bounce around. Suppose we have pre-play signals. If you do a mini bargaining game where guys can demand 2/3 or demand 1/3 or demand 1/2, this is actually the version where the polymorphism 2/3, 1/3 is really the hardest one to dislodge. And run replicator dynamics, picking population proportions at random. Without signals, you get the equal split 62% of the time. Isn't that what I said before? Maybe I didn't get it right. But anyway, 62% of the time. With signals, 98+% of the time. Okay, add more signals, and you're going to get equal split. How about local interaction? There's Jason Alexander. He did local interaction with neighbors in this bargaining game that I told you about. The Magneto guys are equal split, and the other guys are 2/3 and 1/3. This is interaction on the Moore 8 neighborhood. And you can see that these are a few mutants, right? All you need are a few mutants to hit closer together, and equal split takes over in this game. This is a simulation, but you can actually prove this analytically because all the action in these games takes place on the edges, right, of clumps, right? So if you've got a complete analysis of what can happen on the edges, you know what happens in the dynamics, right? And you can prove this result. Of course, you could get a 2/3, 1/3 polymorphism and choose your halfers and drop them in to a clump of 2/3ers or something so that they would go extinct. I mean, there are Garden of Eden configurations that don't always take you to the equal split, but as long as you get a contiguous group of equal splitters, they take over. Dynamic networks. Well, again, it's a timing issue. Let's call the guys that ask more than a half the greedy guys, and the guy that asks less than a half the modest guys. The greedy guys would like to learn to associate with the modest guys, right? Because otherwise they get nothing. And they do. They learn rapidly to associate with the modest guys. And the demand half guys would like to associate with the modest guys or with each other, right? And they do to a certain extent, but the greedy guys have more pressure to associate with the modest guys. So they do better, but then the imitation dynamics gradually wipes out the modest guys, right? They all get greedy. And soon you've got lots of greedy guys, right? And if the timing is such that the equal split guys don't get wiped out too fast so that there's still a few of them around, then they take over. Because the greedy guys run into each other and get nothing, run into the equal split guys and get nothing, equal split guys once in a while run into each other. Okay, so everything works for the equal split. Of course, there are other bargaining games which are much more complicated, right, where things are not going to come out this nicely. So that should predict that, that in fact, if you just give people this, they will always ask for half. And that's true, right? That's throughout all the game theoretic literature that I can find that tests the equal split. This is what happens. Most of these articles just, I mean, it's taken for granted, right, that people do the equal split, but they do this as a baseline to see what happens if you change the game, right? Say this. In fact, I think the experimental literature in game theory shows that the equal split is much more robust than the kind of bargaining game that I talked about, right? That it's used much more generally. It's acquired in some way a focal character that's widely used. What happens if you put the Stag Hunt game together with a bargaining game? Here's Elliot Wagner, who has a forthcoming paper on this. He tried it, and it makes it easier to evolve both cooperation in the Stag Hunt game and equal split in the bargaining game. Right? So putting them together doesn't ruin things. It actually makes things a little easier. Basically because, I mean, part of it is because the Stag Hunt game gives you an outside option in the bargaining game. Let's see, I said that. Two major themes emerge from the foregoing. The first is correlation. Each of these things that I've talked about really are correlation mechanisms. Right? They generate assortment. And of course, there are many other correlation mechanisms that I didn't talk about. So group selection, okay, group selection, correlation mechanism. Repeated games can be viewed as a correlation mechanism in plays of the stage game, and so on. In some sense, everybody's known this since Hamilton and Price got together. The second is dynamics. What would we have if we just did an equilibrium analysis and didn't do the dynamics? Well, we'd miss a lot. So I'll talk a little bit about, so in signals, applied as pre-play signaling in a bargaining game, it turns out that at the end of the game, the signals don't do any good, right? They don't carry any information because everybody's demanding a half then. Right? If you track the information in the signals is used in the middle of evolution to set up correlations of types, right? And that gets you out of the basin of attraction of one equilibrium into the basin of attraction of another equilibrium, and then the information in the signal fades away, but they've done their work. In adaptive networks, what would you have if you didn't look at the relative rates of these two processes, right? And just look at the equilibria? Well, there are just lots and lots of equilibria. There are equilibria where everybody hunts hare, equilibria where everybody hunts stag, where everybody doesn't depend on who visits who or anything, right? There are lots of these equilibria. It's the dynamics that gives you the real bite. Okay? So if I can finish, this is just a little sketch. Construction of a naturalistic theory of the social contract is an ongoing scientific enterprise. Okay? There's no grand picture that I have to paint for you. Yeah.
So, I'm not sure I understood the role of signals in the Stag Hunt game. As if I remember correctly, there is no communicative equilibrium in a Stag Hunt game because it doesn't. I mean, even if I want to cooperate or not cooperate, I always want the other player to cooperate. This always makes me better. So I would never be able to effectively communicate my intentions, right?
Let me say two things. First, the Stag Hunt game I showed you isn't like that, right? The
Right.
Hare hunter doesn't care. But there's a modification of the Stag Hunt where it's a little better for the Hare hunter where if the other guy hunts stag, right?
Yes.
Right? Due to Aumann. And then Aumann gives the argument that you just
Exactly.
gave,
That's
that there
what
will
I
be
mean.
no communication,
Yes.
right? Because everyone will say,
Would like to induce the other
yeah,
to go.
will say what. But of course, say what doesn't mean anything here because these things don't have any meaning. So it's kind of an argument against the evolution of meaning if you want to transpose it into an evolutionary setting. So I looked at that. And you run the replicator dynamics on the Aumann game, and signals still have a big effect. So the rational choice prediction that he makes, giving the argument that you do, doesn't really transpose well into the evolutionary dynamics.
So if I understand correctly, the signals have an effect in some intermediate phase. I mean, during the dynamic, and even if there is no equilibrium where communication is meaningful, the signals help to converge towards cooperative equilibrium.
Yeah.
And the
Yeah,
equilibrium-
and the signals carry information, right? I mean,
No,
if
no,
you
it-
think of information not in in terms of some set meaning, but in terms of conditioning, probabilities conditioning on this, conditional on getting the signal, and unconditional probabilities, right? If they're different, the signal is carrying some information, right? And the signals do carry information. It's enough to make a big difference. Yeah, Mike?
So you mentioned 3 mechanisms on the slides. In words, you mentioned a couple others. Presumably there's still others you didn't mention. How would you go about adjudicating, trying to find out which of these is the most plausible? Or, I mean, is there any...
Well, there can be combinations. They're not mutually
Sure,
exclusive.
Yeah, exactly. Yeah, of course.
And in fact, there is some work on combinations, right, of these mechanisms. So signals go together very nicely with local interaction.
So, but in the nature of the enterprise that you're engaged in is it seems very exploratory, finding different mechanisms, seeing which work, seeing which ones work, seeing which combinations may work better or worse. So it's, but is there any way where we can start? We can expand the set of combinations, but is there any way to kind of prune the set somehow of like
Well,
prune the powers? Take the power set and start whittling.
Depends which social contract you want to explain, I would think, right? Is it ours or is it, ours is hard, right? If it's Myxococcus xanthus, maybe it's easier, maybe things are known, and, you know. So that's a domain-specific concern. I mean, of course you have to, there's a lot of empirical stuff that has to go into it to say which mechanisms are being used and how they got there.